Good evening. My name is Muhammad Aiman Hakim. I will begin this presentation about overcurrent relay for subject power system protection. And my other two members is Muhammad Aiman bin Azizan and Muhammad Hafiz Akmal bin Abdul Halim. So this is about our presentation outline for today. We talk about introduction, objective, problem statement, and so on. So for introduction, as we know, every system should be in a safe condition and situation at all times. So if there is any overcurrent or overvoltage happen, it poses a significant risk to the reliability, performance, and lifespan of the transmission line equipment and associated electrical system. As the result, power system protection are very essential to power system. Is the objective, which is to detect and respond about the relay to abnormal current condition in electrical system from several aspects, which is fault detection, system stability, personal safety, and equipment protection. Problem statement. If a fault happen in the distribution system, it is essential for the relay to close the fault location to be first on the trip. However, if for any reason the nearest protection fails to detect the fault within an acceptable time, a backup protection relay will activate and trip before it. This backup relay is specially designed to stop the fault from spreading across the entire system. The existing protection measures are inadequate for properly detecting and resolving overcurrent conditions. This greatly hampers the maintenance of power system integrity, reliability, personal safety, and the avoidance of downtime. The challenge at hand is to establish robust and effective overcurrent relay protection scheme capable of accurately identifying overcurrent incidents and initiating suitable action to minimize the consequence. By addressing the above aspects, the focus will be on utilizing optimizing technique for coordination of current protection relay to address the fermentation issue. Furthermore, it is important to note that in radial system there is a constraint on the maximum numbers of breaker allowed for overcurrent relay condition coordination, which is typically fewer than 5. That's all from me. Thank you.
Sakma bin Abdul Halim. Today I'm going to continue about methodology. It's begin as you can see in the graph plot, starting from overcurrent relay coordination, go to optimization technique and new constraint for optimal coordination, non-standard characteristic, dual setting protection scheme. Okay, it's begin with a comprehensive analysis of the system, considering factors such as equipment rating, network configuration, and expected fault current. Next, to establish coordination between the relay throughout the system. This coordination ensures that the relay closer to a fault operate first and clear the fault without unnecessary tripping at the relay. Furthermore, testing and commissioning are conducted to verify the proper functioning of the overcurrent relay protection system. Any necessary adjustment of or modification are made during this phase are ensure optimal performance. Okay, for the result is a reliable power system protection scheme is categorized by three key aspects. First, sensitivity. Second, reliability and selectivity. However, the operational system undergoes frequent changes, including variation in generation and dynamic load, as well as potential topological alteration caused by permanent fault or distributed energy resources. Their changes are significant impact on the effectiveness of the power system protection scheme. Continuous monitoring of real-time voltage current system condition for ATC is necessary, and this can be achieved through the use of intelligent electronic device. The gathered data is then utilized to calculate and update relay setting. The objective of this paper is to determine the relay setting for various system conditions based on the collected data. Okay, next. Okay, here is the figure of equivalent system. Figure above depicts a 4-bus system that comprises 4 liners and is supplied by 2 sources, namely the utility at bus 1 and the generator at bus 2. The short circuit rating of the utility and generator are 250 megavolt ampere and 25 MVA respectively. The base MVA is set at 100 and the base kV is 10.5. The lines in the system are denoted as L1, L2, L3 and L4, each with a resistance of 0.02 pu and a resistance of 0.02. The system is equipped with 8 directional overcurrent relay. Okay, here there is 3 types. First is normal system, second is line loss, and that is gonna explain by my friend. Okay, for the normal system, here is the graph and table for the normal system. The test system has global of 8 relay. Depending on the location of fault on line, there are total 10 pair of primary and backup relay are formed as shown in table 1. 3-phase fault current experienced by this relay is also resulting setting for directional overcurrent relay. Table 2 in figure 5. Table 2 in figure 5. Here state in the slide. The relay coordination curve illustrate a relay with a calculated time setting multiplier and plug setting multiplier. To achieve relay condition, ensure proper response when fault is at L3 and L4. Okay, that's all for me. Thank you.
Assalamualaikum. I will continue the presentation. So before that, I will introduce myself. My name is Muhammad Aiman bin Azizan. So I continue the presentation about the result. Generator outage. The sudden outage of a generator can lead to topological change in the system and can also cause variation in the fault current level. In this scenario, the generator connected to bus 1, which is one of the main power source of the system, is disconnected. Table 3 show the information about the primary and backup relay pair for different fault current zone, along with the corresponding fault current. So next, about the generator outage. So there are two figure on the right side, which is graph B is about phase relay coordination curve, and the right side is table 4 show for the result setting for the directional overcurrent relay. So the test system has total of 8 relay, depend on the location of fault online. There are total 10 pair of primary and backup relay are formed as shown in table 1. 3-phase fault current experienced by this relay is also mentioned in table. The result setting for the directional overcurrent relay are provided in table 4. In graph B, the relay coordination curve illustrate after configuring the relay with the calculate time setting multiplier and plug setting value. The achieved relay coordination ensure proper response when a fault occurs on line 1, line 3, and line 4. Next, for the third part of the result, which is a line loss. So line 4 of the test system is removed. Generally, line loss occur uh, due to permanent fault zone wise primary and its backup relay pair as well as a corresponding fault current are given in table 5. The obtained relay settings are provided in table 6, and graph C display the relay coordination curve for the loss of line L4. Adequate relay coordination is achieved for fault occurring on line L1 and line L2. The conclusion about this research is present an adaptive protection scheme for a mesh power system utilizing accurate and reliable numerical direction over current relay. The optimal relay setting, including time setting multiplier and plug setting, are determined through non-linear optimization, considering factors such as fault characteristics, system configuration, and coordination requirement. The general algebra modeling system and a non-linear programming solve are employed to address coordination challenge and find appropriate relay setting. The proposed scheme is verified through a simulation using Mi Power software, ensure its effectiveness and accurate. The result demonstrate the feasibility and effectiveness of the scheme, while also highlight the potential for enhanced precision by utilizing protective relay technique. This research contribute to improve the resilience and reliability of mesh power system. So that's all from our group. Thank you for attention.